day. Ladies and gentlemen, good day class. This is Ndefo Okigbo classes. My name is Ndefo Okigbo. I am a teacher of mathematics, science and engineering. Ndefo classes, lecture 3. We have had lecture 1, lecture 2. We started with forces. Lecture 1 was on resultant of forces in a straight line. Lecture 2, result of forces that are at an inclination. Lecture 3 today is forces in equilibrium. We are studying forces in equilibrium. There are a lot of ways forces stay in equilibrium. When at the time when they are static and there's equilibrium, that means the effect of the forces equates themselves and they remain in equilibrium. So we're starting with a simple force in equilibrium. Example of such arrangement is where things are hooked, hang on like a ceiling, and a load drops from there. As far as it stays, that means the pull by the load will be equal to the reaction by the ceiling, and as such, the two forces remain in equilibrium. Even when there are, like, if we have things like this, remember the Newton's third law, which says that action and reaction are equal and opposite. When equilibrium is established in an equilibrium system, the action and the reaction are equal and opposite. There is a force. There's another force pulling down. This one pulling up. The two forces. If this does not move, that means the two forces pulling, F1 is equal to F2 in different direction. The two forces remain in equilibrium. If the two of them are in the same direction, what they are pulling will follow them. They will move. But since they are not in the same direction and they are equal, then as one is pulling up, the other one is pulling down, and as such, they remain where they are. There will be no movement because they are in equilibrium. Let's take examples like this. A station where this is a ceiling, for instance. Something is hung from the ceiling. It's hung from the ceiling. Let's say this load. Let's say this load is about 4 newtons from the ceiling. As it is, let's say this is A, B, C, then D. If this is the ceiling where the load is hung, now the cable from A to C, because the cable from C to D carrying the load by gravity, by the force of gravity, which is the weight of the load will push, it will be pulling down this point C. As it's pulling down C, BC and AC will not allow that to happen since it is in equilibrium. The force BC and AC will is the direction of pulling, so that they weight the force coming down from CD, trying to pull, which is the weight of the material, trying to pull CD down. AC and BC will refuse. Now the question is that if we know the force at D, which is 4 in this case, how do we get the force in AC and BC? It is simple. Just to bring out the arrangement. This is 4 Newton. This is, let's call this T, the inner force, T1. This is T2. And there are 2 of them are pulling the force 4 Newton to keep it in equilibrium. Now, if at the ceiling, if we know this angle, Let's say, for instance, this angle is 30 degrees. And this one is, let's say, 60 degrees at the ceiling. Then automatically, if we, to solve this problem, we create horizontal and vertical axis. Here, this is, I want to use x axis. This is y, the vertical axis. Looking at this this arrangement here, the angle at angle ABC is 30 degrees. So here now we have also A, B, C, D. The angle B, C, X. The angle BCX will be equal to 30 degrees. That is alternate angles. Angle BCX is alternate to angle ABC. So that means here this angle is 30 degrees. The same way, angle ACX. Angle ACX is equal to 60. It's also alternate to angle BAC. So since we have gotten these two angles now, this is also 60 degrees. That means this will be 30 degrees and this will be 60 degrees. So we can resolve these forces vertically and horizontally. Let's look at the solution vertically. Vertical resolution. We have T1 cos 30. T1 cos 30 degrees plus, because they are in the same direction, plus T2 cos 60 degrees is equal to 4. That's vertically. Then horizontally, we have T1 cos 60 plus T2 cos 30 degrees is equal to, because T1 and T2 are not in the same direction, so plus T1 will be minus, since we have assumed the direction of T1 to be positive. Since we have assumed the direction of T1 to be positive, so the direction of T2 becomes negative because they are not in the same direction horizontally. So plus, then I put minus T2 cos 30 is equal to 0 for that to be in equilibrium horizontally. So that means here cos 30 is 0.8660 T1 plus sine 60, that's cos 60, sorry, 0.5 T2 is equal to 4. Then here cos 60, 0.5 T1 minus this time, because we have opened the bracket. If we open the bracket, cos 30 is 0.8660 T2 is equal to 0. So I have two simultaneous equations, which is any elementary can be solved. If you solve these two simultaneous equations, you get T1 and T2. You get T1 and T2. So with that, two equations and two unknowns, T1 and T2. If we solve these two equations simultaneously, I get T1 and get T2, and the solution has been solved elementarily. It is simple. I can say, okay, I have I can make either T1. The simplest way to do it, let me make T1 the subject. T1 is equal in equation 1, equation 2. In equation 1, I have T1 is equal to 4 minus 0.5 T2 all over 0.888660. So if I get this T1, I can replace it here. I can replace it in the second equation, replace T1 so that I have only T2 throughout, and I solve my problem. If I bring it, I have here 5T, this is T1. So if I bring this here, 0.5 and this 0.5, so it becomes 0.5 bracket 4 minus 0.5 T2 all over 0.8660 minus 0.8660 T2 is equal to 0. So everything is T2. So I can now work out and get whatever I get T2 and get T2. If I clean up this so that there will be more space for me to, so I have 0.5 times 4 is 2 minus 0.25. 0.2 minus 0.25 T2 all over 0.25 T2 is minus 0.8660 T2, 0 squared T2. That's this 0.8 is square of this, because this is equal to 0. From here I get T2. If I get T2, I fix it in and get T1. So, and if I do that, I've solved the problem. Let me look at another one. What in T1 and T2? So that is the first part of lecture 3. The first part of lecture 3.